We're going to take a look at a subspace in this problem. So vector subspace example number 1. U is going to be the set of all vectors that have this form. So it's going to be the set of all vectors whose first element can be written as 2 times r minus s, whose second element is 3 times r, and whose third element is r plus s. And these values r and s are all just real valued numbers. So we can see that U is, looks kind of like R3, but it contains just a subset of the vectors of R3 because everything has been restricted to this form. There are certain vectors of R3 that aren't in this set. So the question we have, given that we've constructed this subset of vectors from the vector space R3, is U actually a proper subspace of R3? So is U itself a vector space? That's the question that we're asking here. So one thing that we can note is that we can actually rewrite this vector in a certain way. We can rewrite this vector as r times the vector 2, because there's a 2 right here. As the second element, we can put a 3 there, and 1 is the third element. And then we can add s times the vector -1, 0, and s, because there's a -1 here in terms of how many s's there are. There are 0 s's here, and there is 1 s right here. So one thing to note is that this vector that we're working with, kind of this general form, can be factored as this linear combination in terms of r times the vector plus s times the vector. And one thing that's interesting to note is that both of these vectors, 2, 3, 1 and 1, 0, -1, both of these vectors are actually elements of R3. And that fact alone helps us solve this problem in terms of determining, is U a subspace of R3? Another thing to note is, since we've been able to write U in this form, we've been able to write U as r times a vector plus s times a vector for all values of r and s. By definition, we've been able to write this set U as the span of these vectors. Because remember what the span means. Span means take all linear combinations of the vectors. Well, that's exactly what we have here. R and s are arbitrary scalars from the reals, so it's very clear that we can write U as the span of these two vectors, 2, 3, 1, and 1, 0, -1. So how does this information help us establish that U is a subspace of R3? Well, there's a theorem that helps us do this. There's a theorem that says if you have vectors v1, v2, all the way up to vn, so some set of vectors, and they are in the vector space V, so you're working in some vector space V, then the span of those vectors is a subspace of V. So there's a theorem that says, given some finite collection of vectors from a vector space, their span is always a subspace of the vector space. So what does that mean for this problem? Well, that means for this problem, what do we have? We established that we have two vectors in R3. Those vectors were 2, 3, and 1, 1, 0, -1. They're in R3. And we were able to show that U is the span of those two vectors, just like it says in the theorem. So that means that U, by this theorem, is a subspace of R3. So this is a very useful theorem. Anytime that we're working with a vector space, if we have vectors from that vector space, and we take the span of them, the set of all linear combinations, we know that we always end up with a subspace of the upper vector space V. For this particular problem, that means that U is a subspace of R3 because we were able to factor our original vector into these two vectors. We noted that both were in R3, and we had the fact that U was the span of these vectors. So that establishes the fact that U is a subspace of R3 by this theorem. Another way to work this problem is actually just go back and establish the properties of the subspace. Remember, when we're working with a subspace or a subset of vectors from a vector space, instead of having to check all 10 properties, there's just 3 properties that we need to check. We need to check that the 0 vector is present, that it's closed under addition, and it's closed under scalar multiplication. That'd be another completely legitimate way to work this problem, is to work through each of those 3 properties and show that they're all true.